What's up? Let's do some math. Let's learn about some division, long division. We all loved it in 4th grade. Well, it's making a comeback. Now we're going to divide some polynomials. But before we do, let's have a little warm-up. Let's refresh our memories on how to divide. So remember, the number that you're dividing by always goes outside. The number that you're dividing goes inside. The number that you're dividing by, in this case 62, is the divisor. And the number that's getting divided is the dividend. The answer is called the, Alex, what is quotient? Nice, very good. Alright, so 62 doesn't fit into 7. So we're going to try to fit it into 73. So it goes in once. So we put a 1 right there. Now we do 1 times 62. 62, we write it right down there. Now we're going to subtract. Alright, 73 minus 62 is 11. 62 doesn't go into 11. Let's bring down that 6. Alright, 62 only goes into 116 once, because I know if you multiply it by 2, it's going to be 124. So let's put a 1 there. Now, let's do 1 times 62, and we write it right there. Now we're going to subtract, and 116 minus 62 is going to be 54. Now we have to bring down the 5. And 62 goes into 548 times. So 62 goes into 545 8 times. 8 times 62 is 496. We subtract and we get our remainder, which is 49. So what does that tell us? All right, that tells us that this number right here, 365 is equal to this number right here, which is 62, times this number, the quotient, which is right here, 118. Alright, but we had some left over. That leftover was the remainder. So that times that plus 62 times 118 plus 49. Alright, that's what division is. And we could use something called the division algorithm to do it. And when we do this with polynomials, we're going to use the same algorithm, and we could use this to factor polynomials, because if there was no remainder here, then we just have 7,365 equal to the product of two numbers, which is factoring. So that's how we're going to use long division in this video, and when we use it with polynomials to help us factor. Alright, so as I stated, as the example in the beginning alludes to, the long division with polynomials is just like long division. Each polynomial must be in standard expanded form, so you don't want to do this with factored polynomials. And make sure you use placeholders with terms that have coefficients of 0. So I'll explain what that means. But pretty much, if you have like x cubed plus 1 and you want to like divide by that, we want to leave some space here for like the x squared terms and the x terms. Alright, and the key thing to remember here is that the dividend, what's being divided by, is equal to the divisor times the quotient plus the remainder. And if the remainder is 0, then you just factored. So let's do one with polynomials now. So first thing we're going to do is see how many times x minus 2 goes into 6x cubed. So for the very first step, we're going to kind of ignore the minus 2 and x minus 2. And I'm going to write the number here, 6x squared, because that number times x gives us 6x cubed. And our goal is to try to get rid of that term and work our way down. Now, we also have to take 6x squared and multiply it by 2 as well, because we're really multiplying 6x squared times the entire divisor. So that gives us a negative 12x squared right here. And now we subtract. 6x cubed minus 6x cubed is 0. Now be careful. When we do negative 19x cubed, you're subtracting negative 12x squared. So sometimes it helps to put parentheses here. So it's really like negative 19x squared minus negative 12x squared is like plus 12x squared. So that would be negative 7x squared right here. Now we could bring down the 16x. Alright, and now we're going to see, okay, what happens when so here's the next step. We're going to just restart it now. how many times does x go into negative 7x squared? So that gives us a factor of negative 7x, because negative 7x times x gives us negative 7x squared. And then you also have to do negative 7x times negative 2, and that gives us a positive 14x. Subtract. All right, I like to put this in parentheses, so I remember to distribute the negative. So negative 7x squared minus negative 7x squared is 0, so we could just put nothing there, or a 0. 16x minus 14x is 2x. Bring down the 4. Now, how many times does x minus 2 go into 2x minus 4? Well, that would be 2, because 2 times x minus 2 is 2x minus 4. Subtract, and we get 0, which means this big ugly polynomial, 6x cubed minus 19x squared plus 16x minus 4, is equal to x minus 2 times 6x squared minus 7x plus 2. So we just used long division to factor. And yes, it was helpful that we guessed right that x minus 2 is a factor, but if you know one factor of a polynomial, you could find the other two by, if it's a cubic, by dividing one out using long division and then taking the leftover quadratic. And now if we wanted to factor this further, we could try using the AC method, or we could do the quadratic formula. It's helpful like if we had a graph of this original polynomial, the cubic one, and we saw that it crossed the x-axis at 2, then we could divide x minus 2 out to see what our leftover zeros were. And if it didn't cross at any other 2 points, then that meant that the leftover quadratic had 2 imaginary solutions. Now it just so happens that this particular quadratic, 6x squared minus 7x plus 2, can be factored because there are 2 numbers that multiply to 12x, or to 12 and add to negative 7. So if we wanted to completely factor this now, we can break up 7x as negative 4x minus 3x, and then factor by grouping. So pull out a 2x here, then you're left with 3x minus 2, and then pull out a negative 1 here, and we're left with a 3x minus 2. And now we could factor by grouping and pull out the 3x minus 2, and we're left with 2x minus 1, and then we have that original factor of x minus 2. So what we just did, I'm getting ahead of myself, but by doing long division, we took this big polynomial and factored it. Granted, we knew what the first factor was, which you can get by looking at a graph, or sometimes it's just given to you. You guess lucky, plug a number in, get 0. But that's why long division is so important, and that's how you do it. So let's do another example. But first, that algorithm, or like this slide over here, this was true with numbers, integers. When we do long division, it's also true with polynomials, and that's kind of what I demonstrated at the end of the last example. So I'll demonstrate the division algorithm again. You can write it in this form, or if we were to divide everything by dx, if we were to take everything here and divide by dx, we would get that. So like 2 different ways of expressing. Now this is important when we, I'm trying to get rid of that exit sign, I don't know how. Not sure. Alright, anyway, if you look on the bottom of the screen, if you ever get a remainder, you want to just add it and divide it by the divisor at the end. Just like if I were to do like, how many times does 3 go into 7? Like what's 7/3? What's that equal to? It goes in twice, but then you get a remainder of 1. So 7/3 would equal 2 plus 1/3, because I take my quotient and then just add the remainder over the divisor. So that also works with polynomials. So here, I did not leave myself enough space here, so I put this here to make a point of that. We want to rewrite this so that I'm going to move that negative 1 there, and then I'm going to leave space for like a 0x squared here, and plus an x term, a 0x term. Alright, that did not come out as well as I wanted it to. Let's try that again. Alright, so ignore this negative one, and we just want to leave space for the quadratic terms that are going to be created and the linear terms. So first, we're ignoring this part here. X goes into x cubed, x squared times. So x squared times x is x cubed, and now x squared times negative 1 is negative x squared. So that's why I left myself that space, because now there's no x squared terms minus negative x squared. So now I get an x squared down here, because we did x cubed minus x cubed, 0, and then 0 minus negative x squared. We can bring that down now. Now, how many times does x go into x squared? X times. X times x is x squared, and then x times negative 1 gives me a negative x. So now when I subtract, I have x squared minus 1 minus x squared minus x. So I'm going to get a negative x, which is just a positive x. And then negative 1 minus 0, because there's really like a 0 right here, gives me a minus 1. And then x minus 1 goes into x minus 1 exactly 1 times. So there's no remainder here. So actually what we just proved by doing all this was the difference of two cubes formula. We had like x cubed minus 1 is equal to x minus 1 times x squared plus x plus 1. So we didn't prove it for all cases, but we showed that we could factor x cubed minus 1 like that, and we know that we could do that from our difference of two cubes formula. A cubed plus b cubed is equal to a plus b times a squared minus ab plus b squared. And that's the formula for a sum of two cubes. For a difference of two cubes, the one that we just did, remember the signs go same, opposite, and then always positive. Alright, let's do one more. So, you take a quadratic trinomial and try to see how many times it goes into a quartic polynomial. So the first number that's going to go right here is a 2x squared, because 2x squared times x squared gives me 2x to the fourth, and then 2x squared times 2x would give me a positive 4x cubed, and then a 2x squared times negative 3 would give me a negative 6x squared. So when we subtract, these terms will cancel, these terms will cancel, and we get x squared plus 3x minus 2 right here. Now, x squared goes into x squared once, so 1 times x squared is x squared, 1 times 2x is 2x, 1 times negative 3 is negative 3. Now we subtract, x squared minus x squared cancels out, 3x minus 2x is x, that's an ugly x, is x, and then negative 2 minus negative 3 is like a double negative, so it's a positive, and we get x plus 1. Now, we are done dividing. Once this last term right here that I erased accidentally with yellow so once this term right here is constant, there's no more variables, you're done dividing. So what that tells us is that this polynomial right here is equal to, so that polynomial right there divided by this polynomial here is equal to 2x squared plus 1, but plus a remainder of x plus 1 over the divisor, x squared plus 2x minus 3. Alright, so if we were to call this the dividend, like f of x, and then this divisor here, d of x, d of x, then we could say this expression right here is equal to f of x, that big quartic polynomial, fourth degree polynomial, over d of x, which is this. We call this part is called the quotient, and then it's the remainder over the divisor, which is also appearing right there. Alright. Alright, synthetic division. Now, synthetic division only works when you're dividing by a linear expression, and you're going to like this a lot better. and it's a lot less complicated, but it only works when you're dividing by a linear expression. So if you have to divide by a higher degree polynomial, higher than 1, you have to do long division. So how it works, you take the 0 of your divisor and you throw it right there. And then you take the L, the big L. Alright, that's like our template for doing synthetic division. Right outside in the upper left hand corner is the 0 of the divisor. Inside, we're going to break this into 2 rows. Alright, the top row is going to be all the all the coefficients of the dividend, so what we're dividing by, or what's getting divided, in order. Now, if it skips a degree, we have to put it as 0. So like if there was like no x squared term, we would have to put a 0 right there. But because there is an x squared term, we put the coefficient there. Alright, so that's how we set it up. Now, we're going to add vertically, so the first thing comes down, and then multiply diagonally. So 2 times 4 is 8, so an 8 goes right there. And we're going to add. Negative 4 plus 8 is 4. And then multiply diagonally. 4 times 4 is 16, that goes right there. We add vertically, and we get 18. Now we're going to multiply. 18 times 4 is 72. 72 plus 5 is 77. So what do these numbers tell us? Well, if we take a cubic, which is right up here, and divide by a linear expression, our leftover is going to be a quadratic. So that tells us that this first term right here is going to be x squared. So all of these variables that have exponents, they all go down by 1. So this is the x squared term, that's the x term, that's the constant term, and that's the remainder. So that means that if we call this function right here f of x, and we say d of x is this, what we're dividing f of x by, is x minus 4, then we could say f of x over d of x is equal to this quadratic, 2x squared plus 4x plus 18, but because x minus 2 didn't go into that cubic evenly, we have a remainder, so plus 77 over the divisor, x minus 4. Alright, so that's what we just did. We just did division, the more efficient way of long division, and we didn't get a 0, so we had a remainder. So we had to put it to the end over the divisor. Alright, and when this number is 0, it's going to make us happy, because that tells us that our divisor is a factor. But in this case, if it's not 0, we're sad, and it's not a factor, x minus 4. You don't have to be sad. Sometimes it's okay to not be a factor. Oh, awkward. Alright, let me look into this. Be right back. Alright, so like I mentioned earlier, if we get a 0 as a remainder, then we know that the whatever we divided by is a factor. So if we had to show that certain factors are factors of a function, we could just use synthetic division. So we could show that x minus 2 is a factor by doing synthetic division on f of x with positive 2. So I'm going to put a 2 there, a 7 there, a negative 4 there, a negative 27 there, and a negative 18 there. So we're going to add and multiply. Add, multiply. Add, multiply. Add, multiply, and we get 0. So that tells us, since 0 is the remainder, x minus 2 is a 0. And specifically, now we know that 2x to the 4th plus 7x to the 3rd minus 4x squared minus 27x minus 18 is equal to x minus 2, what we divided by, times our quotient, which came out to be 2x cubed plus 11x squared plus 18x plus 9. And I got that from doing these numbers over there. Now if I want to show that x plus 3 is a factor, so I just want to do synthetic division with negative 3. So at this point we could just use the quotient because we already divided out x minus 2. So if x plus 3 is a factor as well, it should go into this quotient. So I'm just going to do synthetic division with negative 3 now. Again, only because 2 worked. 2 got a remainder of 0. So I'm going to add vertically, multiply diagonally, add vertically, multiply, add, multiply, and I get another factor that works. So that means now that this part, this cubic factor, could be factored further as x plus 3, because that has a 0 of negative 3, times 2x squared plus 5x plus 3. And then this whole function factored, x minus 2 is a factor. So if we knew two factors, we can use it to factor down this big polynomial like so. Alright, now what if we don't get a remainder of 0? Well, that means f of whatever we divided by is equal to the remainder. So we're going to use the remainder theorem to evaluate functions for certain x values. So given f of x is equal to 3x cubed minus 10x plus 1, find f of 4. So let's do synthetic division. So we're going to put 4 on the outside, put the coefficients on the inside. So 3x cubed, and then there's no x squared term, so we have to put a 0 there. And then negative 10, and then a 1. Now we're going to add, multiply. Add, multiply. That's not true. 12 times 4 is 48. Add, multiply. Add, and our remainder is our answer to the question. If we were to plug 4 in to that function, 3x cubed minus 10x plus 1, we would get 153. Alright, another application of synthetic division. So, recap. How is the remainder helpful for synthetic division? If we get a remainder, r, that's the value of f when we plug x into f. If r equals 0, that tells us that whatever we divided by, so if we divide by x minus k, then x minus k is a factor. That means that k comma 0 is an x-intercept, and x equals k is a 0, or a root and a solution of f of x. So that's just vocab right there. Alright, the last thing, rational zero test. So in all our examples, I told you what to divide f of x by. So what if you didn't know what to divide f of x by and you wanted to factor it? Alright, well, there's literally an infinite amount of things you could try. So first, if you had a graphing calculator, what I would do is graph the function and see what zeros you can tell from the graph. Look at where it crosses the x-axis. But let's say you don't have a graphing calculator, or you're not allowed to use one. What you can do is the rational zeros test. So what that does is that narrows down all the possible zeros of p over q, where p is all the factors of the constant term, so that's the last term when you write a polynomial in standard form, divided by all the factors of the leading coefficient, plus or minus. So any real, rational zero, well, if it's rational, it has to be real. So any rational zero will be in the form of p over q. So let's look in this last example. So let's say I said completely factor 3x cubed plus 2x squared minus 19x plus 6. Well, I don't give you any factors. Well, you can't factor by grouping, because when you pulled out the x squared in the first two terms, it came out to be 3x plus 2, and that's completely different from negative 19x plus 6. So we would have to try all of the rational numbers in the form p over q. So all the factors of 6, the constant term, divided by all the factors of 3. And they're all listed right here. Luckily, if it's a cubic, once you find one, you can do the quadratic formula to do the other two. So you should never really be doing synthetic division with fractions, all right? Unless you're really desperate. So let's try. So let's try 1. When you try 1, we're looking for a remainder of 0. We're going to try 1 because it's just easy to work with. So we're going to pull down a 3, multiply, add, multiply, add, and right now I could tell that we're going to get a remainder that's not 0. So I know 1's not a factor. And then if you tried negative 1, that wouldn't work either. So I'm going to try 2 now. So I made this question, and I looked at a graph, and I could tell that 2 is a 0. So that's why I'm jumping to that, to try to save you guys time. But in real life, you'd have to keep trying until you found one. So we bring down the 3, multiply, add, multiply, add, multiply. So we get a remainder of 0. Yay, that's awesome. So that means x minus 2 is a factor. So now I could take g of x, and I know that g of x is equal to x minus 2, because 2 is a 0, times 3x squared plus 8x minus 3. Now, I don't need to do synthetic division because I have a quadratic. You should never do synthetic division with the quadratic because you could do the quadratic formula, or in this case, just factor. So look for two numbers that multiply to negative 9, and add to 8. So you could do 9 and negative 1. So if you factored this, it would come out, this part, it would come out to 3x minus 1 times x plus 3. And then the other factor was x minus 2. So now we have this completely factored. Alright, now we might as well graph g of x. So we got a little room over here. So this will be the last thing we do. So we're going to plot our zeros. We know there's a 0 at negative 3 over here. We know there's a 0 at 1/3 from this factor. And a negative 3 is from that first factor, and a factor of 2. Alright, we know that since the leading coefficient is positive, right, it's a 3, that's going to rise to the right. And we know that since the degree is odd, it's going to fall to the left. And also, you could plug in 0 and find g of 0, and that's your y-intercept, because every point on the y-axis has an x-coordinate of 0, and you get 6. Alright, now we're going to connect the dots. And all of our zeros have multiplicities of 1. So that means our graph is going to go through all the zeros. There's going to be no bounces or anything. So let's complete the graph, and that's what our sketch would look like. Alright, you got to hit the zeros, you got to respect end behavior, find your y-intercepts, and don't do more than n minus 1 turns. Alright, thanks for watching this long video, but there's a lot of good stuff in there. Everything right here is just kind of like the steps to graphing a polynomial that I just went over. So if you want to jot that down now, it's there. And that's it. Thanks for watching.